All right, let's just jump right in. For decades, one of the biggest, most stubborn mysteries in all of physics has been dark matter. We know it's out there. I mean, we can see its gravitational effects pulling on galaxies, but we have absolutely no idea what it actually is. It's like this cosmic ghost that makes up a huge chunk of our universe. But here's the thing. What if we've been looking for it in completely the wrong way? Seriously, think about that. What if the answer isn't some exotic new particle hiding out in the shadows, but something much, much more fundamental about the very fabric of reality itself? In this explainer, we're going to explore a pretty radical new idea that flips the whole search for dark matter completely on its head. To really get this new idea, we have to rewind. We've got to go all the way back to the beginning, to Albert Einstein and his theory of general relativity. This is the foundation, it's our current rulebook for how the entire universe works on the biggest scales imaginable. So Einstein taught us that reality is essentially made of two big interacting things. On one side, you've got space-time. Just picture it as the literal stage of the universe. And on the other side, you've got energy. That's, well, everything else. All the matter, light, and forces. These are the actors on the stage. It's a beautiful dance, really. The actors, with their movements and mass, tell the stage how to bend and curve. And in turn, the curves of the stage tell the actors how to move. It all boils down to this incredibly simple yet totally profound equation. The geometry of spacetime on the left is determined by the geometry of energy on the right. Simple, right? This is the fundamental dance of the cosmos. But here's the problem. We seem to be missing most of the dancers. When we add up all the energy in the universe, all the actors on the stage, we come up shockingly short. And for almost a century now, our search for all these missing pieces has focused entirely on just one side of that cosmic equation. And this is where the scale of the mystery just kind of slaps you in the face. The stuff you and I are made of, all the stars and galaxies we can see, normal matter, that's only about 5% of the universe. Just 5%. A whopping 27% is this mysterious stuff we call dark matter. It's like the invisible scaffolding holding galaxies together that we just can't see or touch. So, for decades, the most logical assumption has been that dark matter must be some new, undiscovered particle, a new actor we just haven't met yet. And this idea kicked off this massive worldwide hunt with these incredibly sensitive detectors built deep underground, all trying to catch just a tiny glimpse of this elusive particle. And after all that time, all that effort, all that money, this is what we have to show for it. A big, fat zero. Nothing. Not a single confirmed detection. And this complete lack of success is now forcing some physicists to ask a really uncomfortable question. Did we make a wrong turn somewhere? And this is where a bold new theory comes into play. It suggests that maybe, just maybe, the problem isn't a missing particle at all, but a fundamental misunderstanding of the stage itself. This quote really gets to the core of the whole new idea. What if dark matter isn't a type of energy, not an actor on the right side of Einstein's equation? What if it's actually a property of space-time itself, something happening on the left side of the equation, the side we've basically been taking for granted this whole time? This new model is called changing space, and it proposes that nature isn't really divided into two things, the stage and the actors. No, instead, it's one single, unified, dynamic object. And the key new ingredient here is the idea of elasticity. It suggests that space isn't just this passive backdrop. It can actually stretch and ripple and wave in more complex ways than we ever imagined. So, okay, if dark matter isn't a particle, then what is it in this new model? Well, the answer completely changes the game. It suggests dark matter is actually a wave. So here it is, the fundamental difference, side by side. In the standard model we've been using, dark matter is a particle, a type of energy we have to hunt for. But in this new changing space theory, it's a wave, a property of space-time itself. This means we should stop looking for particles and start looking for its huge, large-scale, wave-like effects on the cosmos. It's a total shift in both what dark matter is and where we should be looking for it. So, what would these waves even be like? Well, you can think of them as being pretty similar to the gravitational waves we've already detected, but there are some really key differences. These dark matter waves would travel much, much slower than the speed of light and have absolutely enormous wavelengths. They wouldn't be caused by something dramatic like colliding black holes. They'd just be a natural, fundamental property of this newly elastic space constantly rippling through the universe. The implications of this are, well, they're huge. If this theory turns out to be right, It means we can stop building bigger and more expensive particle detectors to find dark matter. The answer isn't deep underground, it's written right into the geometry of the cosmos itself. And this theory makes a very clear, very testable prediction. The scientist behind it is so confident, he states flatly that the particle hunt will continue to find nothing, because there's simply nothing there to find. Now that is a bold claim that puts this idea in direct opposition to decades of mainstream physics. And that kind of brings us to our final thought here. For nearly a century, we've been searching for a missing thing. But this new theory asks us to consider a totally different possibility. Maybe the mystery isn't about what's moving through space, but about what space itself is capable of doing. What if the ghost in the machine isn't a ghost at all, but a feature of the machine we just never understood until now?